In this unit, we'll look at what shockwaves are and where we might expect to encounter them. We have a complete section on shockwaves coming up in section 3 of the course, so here we'll just introduce some of the ideas. The title of the course, Hypersonics, From Shockwaves to Scramjets, suggests that we should look at shockwaves before we look at scramjets, and that's what we're about to do. In this subsection, we'll introduce shockwaves, and in the next subsection, we'll introduce scramjets. We'll restrict ourselves to shockwaves occurring in gases. Shockwaves can occur in a flow when it's moving at a speed higher than the speed of sound, or in a gas through which an object is moving at close to the speed of sound or in excess of the speed of sound. They don't have to appear, but they can. Therefore, we expect to encounter shockwaves in flows that are transonic, supersonic, or hypersonic. We can also generate shockwaves that move at supersonic and hypersonic speeds through stationary gases. In fact, the cracking of a whip generates a shockwave as its tip travels faster than the speed of sound. You hear that as the crack of the whip as the shockwave passes by your ears. So what is a shockwave? Well, a shockwave is a very thin region in a flow where the gas properties, such as pressure, which we'll call P, temperature, which we'll call T, and flow speed, which we'll call V, all change very abruptly. If a shockwave was travelling across this room right now, the pressure and temperature of the air would increase as the shockwave passed, and all the air would be travelling to the left behind the wave. So after the wave had passed, I'd be in a region of high pressure, higher temperature, and the air would be blowing away to the left. Of course, the shockwave would travel across the room much more quickly than that because it would be travelling faster than the speed of sound. Also, if the shockwave was generated by a blast or a sonic boom from an aircraft, the shock would be followed by an expansion that would soon return the air to its original condition. Now, if there was a hypersonic flow blowing through this room right now, then apart from it getting a little uncomfortable for me, and we'll ignore the fact that I'd be blown away, a shockwave would form around me. Everywhere upstream of the wave would be at the oncoming flow conditions. Because I'd be a big blockage to this nice hypersonic flow, a big curved bow shockwave would form around me. This is a little bit like the bow wave that forms in front of a ship travelling through the ocean. Behind the shockwave, the pressure and temperature would be increased and the speed of the flow would be decreased. Let's do one more thought experiment. What if I was travelling at a hypersonic speed through the still air in this room? Then a bow shockwave would form ahead of me and would travel through the stationary air ahead of me. The model that we'll use in section 3 of the course has the shockwave being a discontinuity. That is, the properties of the gas change instantaneously as the flow passes through a shockwave or a shockwave passes through a gas. We'll finish off this unit with this historical photograph. You normally can't see shockwaves with the naked eye, but in the late 1880s, Ernst Mach presented this photograph in a paper given to the Academy of Sciences in Vienna. And yes, that's the Ernst Mach after whom Mach number is named. This is thought to be the first published photograph showing a visualization of shockwaves. The photo is of a bullet flying from right to left at a supersonic speed through still air. As the bullet travels to the left at a speed higher than the speed of sound, the air ahead of the bullet does not yet know that the bullet is approaching. It can't know about it because the information that the bullet is approaching only travels through the air ahead of it at the speed of sound. Mach used a technique called the Shadowgraph Technique to make the shockwaves visible. This technique uses the fact that the density of the air changes as it passes through the shockwave. This density change causes the light to refract as it passes through the gas, and this leads to light regions that indicate regions where the density gradient changes, such as through shockwaves. The shock waves in this photo are the inclined white lines. Don't confuse them with the vertical straight lines that are just the wires that Mark used to trip the shutter of the camera. We can also see some density variations in the wake that show up the wake of the bullet. So now hopefully you have a bit of an idea about what shock waves are. As I said, we'll go into much more detail in section 3 of the course. In the next subsection, we'll have a look at what a scramjet is.